Okay, hello everybody. So yeah, it takes a while to set up the class with Moodle and everything, but so I wish I could do that sooner, but here we go. So I've surprised a few of you who went and looked at the notes of the class and saw that it was about Taylor series. So don't worry, you haven't seen Taylor series yet. It's just that I messed up. So I changed it. Oh, is that? Right, okay. It's working. All right, so let's continue on our journey with chapter 4. Yeah, so now we should probably finish chapter 4, maybe start a bit of chapter 5. So we're digging deeper and deeper and deeper into solving linear systems of equations. So today is a mismatch of many different things. So for instance, oh yeah, there was yeah, so you did mostly well at for the quizzes, the small quizzes online. So I won't spend too long, spend some time on that. So it's fine. I'm happy with the results. If you have a question about it, just ask me later. Yeah, so we're continuing with the properties and operations and matrices. Okay. So some properties of transposes that I haven't told you about yet. So one is so the transposition of a sum. If I have A plus B transpose, then what do I get? I get A transpose plus B transpose. Move left to the reader. This means when I write this, it doesn't mean you have to do it. It just means that I won't take time to do it. So that one is pretty simple. More complicated one, transpose of a product of matrices. If I have A B transpose, everybody knows what I get. I hope at least one of you does. Yeah, exactly. So I apply the transpose to all of the elements, but also I flip the order around. Oops. Oops. Yes, B trans. A trans. Last year I did spend some time trying to prove this myself, and I got super confused. So if you want to go and try it for yourself, go ahead. So yeah, I think it shouldn't be too difficult, but yeah, it can be confusing at some point. All right. So that was properties of transpose. So know them, learn them by heart. This is it. It pains me to say that, but yeah, that's the way to go. You just have to learn stuff by heart to know how to manipulate them. Okay, special matrices. By the way, you can take pictures as much as you like, but I post everything after the class. But you won't see my nice face on the side. Maybe that's a bonus. So of course, like in anywhere, some elements are more interesting than others. So let's go with neutral elements. Yeah, so the zero matrix, as the name suggests, it's a matrix filled with zero. And we say it's the neutral element of addition. Of course, there are an infinite number of zero matrices because I haven't told you what the dimensions are. And you use the dimensions you need for your own problem. So for instance, if I have A, B, C, plus the zero matrix, that would be 0, 0, 0. And this would give you, of course, A plus 0, B plus 0, C plus 0, D plus 0. So you get the same thing. So what do we mean by neutral element? We mean a neutral, an element which if you use it in some specific operation, then it doesn't change the other element you started with. So here I use it in an addition and it doesn't change the other element. Somebody knows what the neutral element of matrix multiplication is? Yes, one is a okay answer for arithmetic and scalars, but yeah, for matrices, it's identity matrix. So we write it I, capital I. It's the neutral element of multiplication. And of course, again, I have to pick a matrix that fits the size of the other matrix I'm using. So let me give you an example. So if I have a 2 by 3, so let's see, I have F. So what size should I use as an identity matrix? 3 by 3, yes. So that's what I need. And this is what it looks like. And this matrix has a magical property of keeping the starting matrix intact. So let's show you what we mean. First of all, what are the dimensions? It's 2 by 3. And I might multiply by a 3 by 3. So I should get as a final answer 2 rows and 3 columns. And you haven't seen my finger there, but and 3 columns. I should use my pointer instead. All right, and let's just do that. So the first element would be simply A times 1 plus B times 0, C times 0, so I get A. Then B times, then A times 0 plus B times 1 plus C times 0, so I get B. And here, for instance, I get A times 0 plus B times 0 plus C times 1, so I get, and same thing for the second row, so D times 1, I get D, plus E times 0, F times 0. So And what I can also do is not post-multiply, but pre-multiply by the identity matrix. If I want to do that, what size do I need?
2 by 2.
Yeah, 2 by 2. So again, if you just write I times something, it's I with certain dimensions, and you have to make sure that the dimensions fit. Okay, I will write it 1, 0, 1, 0. And let me just, it gives me the same thing. Computers are nice. Yeah, so note. Dimensions. Another special matrix. So questions about the neutral element. So zero matrix, we don't use it all that much. Identity matrix, it pops up a lot, but we don't really care because once you have it, then you can pretty much just remove it and it doesn't change anything. Diagonal matrix. So it is a square matrix. With zeros. Diagonal elements. So for instance, so it's squared. So here I pick 3, 3, and something like 0, 0, 1, 4, 5, as long as the rest is 0. And usually you can use this to scale things up because, yeah, here you sometimes in econometrics, not going there. Question. Is the zero matrix diagonal? Like this, for instance. Yes. So yes, if it is squared. But actually, I don't want to put my hand in the fire. The thing is, some people may use many types of matrices in different ways, and maybe they have a diagonal matrix that's still not squared. But in my definition, it's a square matrix. All right. The definition that you're going to see most often. So, and then second question is the identity matrix. Diagonal. Yes, all the time. Because it's squared and it just has one element. No, now it's all of diagonal elements. Yeah, so this is lower triangular and upper triangular. Yeah. Oh, by the way, so you had a question like last class, I think, about multiplying vector. So I think this was yeah, vector product we were talking about. I checked it. Yeah. There are many different types of products in higher dimensions, so each do different things. So now we stick with the, but I do have a bunch of notes about graphical interpretation, and I think I'm going to skip over them. But if we have some time to fill up at the end of the semester, I could have a chat about it. All right. Matrix. So it is a square matrix, which, when multiplied by itself, yields itself. So this is many, many, many words to just say this. So AA equals for matrix. And they look magical, at least to my eye. So I wouldn't know that I could come up with them on my own, but yeah, they're neat. Yeah, there are ways to build idempotent matrix. Yeah, there are general forms. So if I multiply these two things together, so let's just have fun and look what we get. So here I get, so I'm just going to redo element by element. So I get 6, so 4 times 4 minus 12. So here I get 12 times 4 minus 3 times 12. And here I get 2. Yeah, minus 1 times minus 1. So let's just see 2 plus. What am I doing there? Oh, no. Yeah, so minus 4. And then plus 3. And then I get minus 12 plus 9. And you can, so this is 16 minus 12, that's 4. This is 1. And this is 12. So these are quite neat. Question: is the identity matrix? Yes. It's like a quiz game, and I have the answer before I have the time to finish my question. Yes. And the zero matrix, if it's square, then yes, it's identical, of course. So now let's dig into more dark territories of matrix algebra. Of course, I'm usually mostly following the book, but I'm skipping over many details because the book is very long. So I'm presenting what is most important to my opinion. So in general, AB isn't the same as BA. So we have seen this before. But as we know in scalar algebra, yeah. PB equals BA. So here I'm saying what may be surprising to your eyes of early discoverer of linear algebra. Yeah, so in scalar algebra, PB equals 0 implies that either A equals 0 or B equals 0. But in matrix algebra, that's not necessarily the case. Let me just write this. Another magic case. So for if I have 2, 4, 2, then I multiply this with minus 2, 1, 4, minus 2. Then what do you get? Well, we get a 0 matrix. We get a squared matrix, but let's just compute it for ourselves. So this is minus 4, and then plus 4. This is 2 times 4, 8, minus 8. This is minus 2 plus 2. And this is 2 times 4, 8, minus 8. And of course, I get 0, 0, 0. So that's also pretty surprising. There is one thing that's going on there. Is that these numbers, they sort of look like each other. You see that here I have multiplied this first number by minus 1, and here I have multiplied the second number by minus 1. So it doesn't work for everything, but you see that even if you start with a non-zero matrix here and a non-zero matrix here, you can end up with a 0 matrix when you multiply. Question. Does C times D equals C times B imply that D equals B? And I'm going to let you think about it. And what do you think? Yeah, not necessarily. A good example of this is 0 elements, or yeah, both the identity matrix and the 0 element can give rise to 3 weird things. Because if I multiply this, So CD, CE. So if I multiply this by, so no. Example. This multiplied by the zero matrix that gives me the zero matrix. But of course, the zero matrix is not the same as this matrix there. So I multiplied by the same matrix by different other matrices, and I get the same result. And same thing for the idempotent matrix. So here, if I multiply this by an identity matrix, then I get, of course, so these are very peculiar properties of matrices, and you have to be careful when you manipulate them, not to make hasty judgment about what's going on. Yeah, one other. Am I going too fast, or you have time to copy? And yeah, okay. Yeah, sometimes I may go too fast and I not realize. Last special matrix, or some special matrix are coming, but one important one is symmetric matrix, or the symmetrix. No, that doesn't exist. Maybe we should invent this for the symmetrix. So that's I'm guessing that you can guess what it is. A square matrix. A is symmetric. Oh, I hope I don't start writing symmetrics everywhere. If A transpose, so for instance, 1, 2, 2. Since, of course, if I take the transpose, I get the same. And of course, zero matrix. No, actually, not the zero matrix, the square zero matrix. Well, yeah, I'm not going to talk about the zero matrix. Not such an interesting. Of course, the identity matrix is symmetric. All right. Okay, so these have nice properties too. I'm just laying everything out there now, and then when the time comes, we can start discussing more in detail what's up with that. Okay, now inverse of a matrix. So now the fun starts to happen. So what is the inverse of a matrix and why do we need it? So no. So I haven't talked about, so I've talked about addition and of course implied that you can of course subtract matrices. I've talked about multiplication. Can you divide matrices? No, but you can multiply by the inverse of a matrix. So this is what we're going to discuss. In matrix algebra, division is not defined, but multiplication by the inverse is. I should say this is how when we talk about inverse, we always talk about multiplicative inverse. Because in a way, the inverse of the additive inverse of a matrix would just be minus that matrix. But you're never going to see this if, anybody say it's the multiplicative inverse of a matrix. Everybody assumes it. So yeah, I'm just going to say a multiplicative inverse. Always assume. And so why do we need the inverse? Well, it allows us to get back to the neutral element. So that's what an inverse does. Yeah. So if you have an operation and by the way, I don't know this. Not too sure. I think the name of this is a group or something. When you have some properties and elements and operation and inverses on the elements. But anyways, that's higher level stuff. But anyways, we have inverse in matrix algebra. So that's the only thing I'm going to say. Okay, so given a matrix, n by n matrix, its inverse is a minus 1, such that a minus 1 equals to a minus 1a equals to the identity matrix, and I'm going to say it's n identity matrix, meaning the identity matrix that you get, of course, as n rows and n columns. So if you think this is not trivial, I agree with you. So I'm not going to discuss too much why this is the case, but so what you have to know is that a times its inverse is equal to the inverse of a times a. It could have not been the case, but it is the case. And we're going to use this in our demonstrations later. Only square matrices with, and then this is much later, but still I'm going to say it right now with linearly independent rows. Yeah, so if you, it's true. So if you say that every row, column of the matrix is a vector, or every row of the matrix is a vector. But so, yes, strictly speaking, that's the case. I'm guessing that if I go wrong, sometimes you're. No, but it's good. I like to improve every year. So if I make sloppy statements that you know are false, please tell me. All right. Oh yeah, sure. Yeah, that's the whole point. Yeah, we do look at a bunch of, but I'm sure we're not going to look as deep into detail as you would like, but yeah. In the book, they have sections that are interesting, but that go in much deeper, but that I thought for economists, it's it's not the thing that you use most of the time. Yes? Yeah, I'm not teaching this to you. No, I'm going to teach you. That's computing inverses is something that a non-negligible number of fraction of the mathematicians in the world work on. Okay, so, or not exactly necessarily computing inverses, but solving systems. What? Well, I'm going to ask you to compute inverses. Yeah. So, but when you have it, then you know that if you didn't make a mistake, then you know by definition that if you multiply it with its own matrix, then you get the identity. So, but yeah, computing the inverses, and later on, it's resolving systems of equations. So this is the bread and butter of so many mathematicians. We're going to delve into that. So yeah, I'm going to say what we mean by this. Can have inverses. Example, for a 2x2 matrix. A equals ABCD and A inverse. I'm just going to tell you what this is. So A inverse is 1 over AD minus BC. Oh, sorry. What? Yes, sort of, yes. So yeah, anyways, that's the inverse of a 2x2. So you Kramer's rule is one way to compute it, but yeah, it can be many times d. So you here d minus b minus c and a. So I know I didn't expect you to know how to compute the inverse. I just gave it to you, but let's check that this works. So a minus 1 gives us what? So of course, this is a scalar, and a is a 2x2, and a minus 1 is also going to be a 2x2. So I have a 2x2. All right, so here I get AD minus BC. I put some shortcuts and I shouldn't do that. And then the second one is A times minus B, so minus AB. And B times A plus BA. Here I get C times D minus DC. And finally, I get C minus B minus CD plus DA. And this is all multiplied, of course, by this. So then here I have 1. So let's just put this inside. So here I'm going to get 1. Here I'm going to get 0. Here I'm going to get And here I'm going to get again pure black dark magic. How did we get that? Well, we're going to learn how we were able to compute these things. Note, this little thing here is not by accident. This is called what? Yeah, the determinant. A. So write this. Okay, so question. What if AB equals this? Can I compute the inverse of A? Yes. So this thing there is fundamental. It's what determines whether my system has a unique solution. If not, it means that the matrix which represents the system cannot be inverted. So if this was a set of, say, coefficients that would that represented something like two lines, then zero determinant essentially means that the two lines are straight lines, that are parallel lines. So for instance, so what if this is then the determinant is 0 and the matrix cannot. So back when when I showed you 2 classes ago that you could go from a system of linear equations to a matrix representation. So I had something like A x equals, I think it was equal D. So A here is the matrix of coefficients, and D was the vector, and X is the all the variables I want to, which I want to find the intersection of, and D is the constant terms. So what if A? So let me show you. So for instance, consider A equals 1, 2, and then 2, 4. So what does that mean? Well, if you remember, this meant that whatever the constant term was, if I had the coefficients of my two equations that look like this, where one is just multiplied by 2, or the other multiplied by 2, then what did I find? I found that I would have parallel lines. And then, so I would have either no solution at all or an infinite number of solutions. So the determinant in this case is AD, so 1 times 4. And you would write it this way. So the determinant is of A would be written this way, minus 2 by 2. And what do we get? You get 0 determinant. So this determinant is the key to everything. So once we know the determinant, we know once we know that the determinant is non-zero, this is how we're going to know that we can find a solution, a unique solution to a system of linear equations on it. Right? But this is, we're going to get there. I'm just, laying the field. Properties of inverses. Yes, just to comment. So in this case, the linear system of equations. Whoa. Equations would represent two parallel lines yes, have either zero solution or an infinite number of solutions on top of each other. Infinite number of solutions is a more mathematical way of saying it. All right, so properties of inverses. Here, let's just be fancy and use one. Only square matrices have inverses. But not all of them have. For instance, what is I say that? Yeah. Oh yeah. Okay. Being squared is necessary, but not sufficient condition. IE is yeah, which means being squared is a necessary but not sufficient condition. Note, so this is for your own knowledge. If you're stuck with a matrix that cannot be inverted, so you have other types of matrices, so of other type of inverses. So more definitions. Inverses exist, such as the more and Rose was, you know who he is? So he won the Nobel Prize in Physics in 2020. So yeah, so there are, so in cases where the determinant is zero or when the matrix is not squared, are you stuck? Can you do nothing? No, mathematicians have thought of other ways to still do what you want to do if you wanted, for instance, to multiply by the inverse of a matrix. But of course, this is much more advanced. We don't care about it. It's just for your own culture. Two, a matrix. Yes, so not like the example. A matrix which has an inverse. Is called non-singular. which is funny because if you have an inverse, then you can find a singular solution or a unique solution to the system, but yeah, that's how it's called. And a matrix which doesn't have an inverse is called singular. And 3, each inverse is unique. A minus 1. You cannot say A minus 1 is an inverse of A, you say is the inverse of A. And A is A minus. Again, so if we work with matrices all the time, we may take these things for granted, but when you think about it, nothing of that of these things is necessary. You could have many inverses or many different things could be going on. Well, actually, not necessarily. So let me just prove 3. And we're going to use this thing there, using this. So if I didn't give you that, you couldn't prove it. But if I told you that this is the case, then it's possible to prove it quite easily. So we're just going to, much of the time in mathematics, when you want to show that something is unique, so you say, well, let's imagine it's not. So let's start with 2 different things that have the same function and show that in the end, these 2 things must be the same. So let's go ahead and do that. So AB. Oh yeah, I missed the. So assume that A has 2 inverses, 2 distinct inverses, or 2 inverses. Maybe they are distinct, maybe not. B and C. So now we're just going to, so this proof is much easier than the other ones that we did before. So yeah, let's start. So AB equals what? It equals the identity. So this is just the definition of the inverse. And what we're going to do here is, so you see that we have A here. And what we can also do is pre-multiplied with its inverse to get the identity matrix. So what we're going to do is pre-multiply by the matrix C on either side. So we're going to see C times AB equals to C times I. So anytime you do stuff with matrices, the order of operations matter. So what you can say is, I have some matrix on the left side, I have some matrix on the right side. Let me say pre-multiply by C on either side, or you could also post-multiply by C on either side, but you have to decide. You cannot like mix them both, because we've seen that it makes a difference purely just because of the dimensions. So this, we can do that. And yes. Here, what we're going to use is the associativity of multiplication. Yeah, so this is equal to this, because we've seen that C times AB equals to CA times B. Or you could just write CAB, but I think it's so we write it this way to really highlight this. And just to make me realize that you understand what's going on, you can say using the associativity of matrix multiplication. Yeah, and then we're almost done. So CA, it's equal to C is equal to what? I. Good. So then, and of course, if I pre or post multiply by I get the same thing. So equals. But so note that the reason I was able to prove this, it is because here I'm able to. So AB, if B is a inverse, then AB is I, and if C is an inverse, then CA is I. So that's this property right there. Properties of inverses. What time is it? 13, so go until 2:30. So oh yeah, we're good. Oh, I just did am I repeating myself? Yeah, I just did that. So oh yeah, other properties. A inverse inverse. What does that give me? It's equal to A. Since A is the inverse of A minus 1, and so A minus 1 is the inverse of A, then if I take the inverse twice, I go back to what I started with the products AB inverse. And this is exactly like with transposes. So what I have to do is distribute this inverse inside, but also flip the order. So all these things, there's no way that we ask any question. We just say, yes, this is the case. And finally, A inverse transpose equals to A transpose inverse. All right. Yeah, so I had some geometric interpretation of vector operations, but yeah, as I said, it's not that pertinent for economics, so I think we're going to leave it there. We still have 15 minutes, so we can start the next chapter. Questions about how we did? So it's really just definitions and operations and definitions and operations. So I know your head must be a bit full, but yeah. The trick is to practice and practice and practice, and know that. So about proofs, I may ask you small proofs, but in my opinion, they are doable. So they're not the more difficult kind. So anyways, you see, you try them and you see what you find. Where is it? Where is it? Okay. So here we go with solutions to linear systems. What can I say in a few minutes? Yeah, I'm a bit repeating what I just said, but all right. So chapter 5. Solutions to linear system of equations. Recall that linear system of equations has a unique solution if all equations are independent of each other. For instance, we assume we have the following system. X1, X2 equals 1. And then I'm lazy and I don't even care about finding some other line. I just multiply everything by 2. So 2x1 plus 4x2 equals 2. So I make it seem like I have many equations or 2 equations, but really I just have one because I just multiplied it. So sorry, thank you. So of course, the second equation is just the first one multiplied by 2. So represents exactly the same line. The system has an infinity of solutions. So we say it is underdetermined. If I keep the same thing, but instead of having 1 and 2, I have 1 and 4. So if this is 2 lines that are exactly on top of each other, then these are just exactly parallel, but they never intersect. So how many solutions do I have? I have no solutions. So represent that are parallel. They never intersect. They have no solution. So the system has no solution. So there is no pair of values x1, x2, which you can give me, which are going to satisfy both equations at the same time. So what I could do is, for instance, so assume that x1 star, x2 star is a solution. So that would mean that if I substitute 10, I would get x1 star, x2 star. And then what I can do is just divide the second one by 2. So I could just get so I would find that x1 star plus 2x2 star equals 1, and x1 star plus 2x2 star equals 2. So, of course, no solution. Yeah. Of course, this is. So please don't show this and say, yeah, my professor said this was fine. No, it's not fine. So what's the similar thing? What's the similar story between the both situations? Well, I've changed the constant terms there, but the problem was not with the constant terms. The problem was with the coefficients there. In both cases, I had the set of coefficients for equation 1, which was just a multiple of the set of coefficients for equation 2. So yeah, let's put it in matrix form. Let's go with the general case. So if I have, yeah, this is what I'm going to do generally is I'm going to have numbers for rows and letters for columns. B1, B2, B1, B2. Times X and Y. Yeah, so you consider general. And now we're going to see how we where this is going. Yeah, I think this is a nice thing because it minimizes the number of. So I just need 2 indices, and I have all B's for the second row, all A's for the first row, and then this is 1, 2, 3. So I think that this makes things clear. How do I go into this? I think it's. Yeah, let's. All right, let's do it. Okay, 5 minutes. So as we said, so the problem is if the second row is the coefficients of the second row are multiples are how can I express this? If the coefficients of the second row are the are the coefficients of the first row, multiplied by the same constant. So how do you express this? Well, imagine that I have, take the constant can be anything, lambda, for instance. So it's problematic if I have A1 lambda equals V1. And if I have A2 lambda equals V2, right? So this is exactly what we were saying there is if I multiply the coefficients by the same number, then this creates a problem. And then what can I do? Well, I can just say, so the problem is, let's divide by both the first equation by the second. So I would have A1 divided by A2 times lambda divided by lambda, which would cancel out. Would give me B1 divided by B2. Or A1 B2 equals B2 A1 B1 B2. Or A1 B2 minus B2 A1. So this is exactly what we said earlier. It's that this quantity there is the determinant. If it is 0, then this is what this means to be to have problem. Okay, so yeah, I don't know if it was a good thing to do this in the last 5 minutes, but here we go. So questions just before we leave. So I'll post some exercises for the TA session, and don't remember to work on the homework. That's a good question. I haven't thought of that. It would be better if no. I mean, since we cannot represent the limited set of it would be better if you describe it like by a statement like to have describing the separations. It's such as like the initial numbers, then divided by 2 yeah, you can definitely that you want. But then then these two show the prices and the
So like, I don't understand X value that you put or the result that you put in, like in your set. If you have something different, X such that X is the number at the end, and then you have like the X 4X, would you put every multiple or in a set, or would you put X because like every single number because every single number is like multipliable by 4?
Oh, yeah. So if you have a set that set states x has to be natural and x times 4 has to be natural, then what do you get? You get the natural numbers.
You get every single number?
Yeah, because so if I multiply, say 3 times 4, I get 12, it's still a natural number as well.
Okay.
So it's, of course, you get a natural number. But when you divide, it's a different story.
When you divide, it's going to be only the result of the
Yeah,
division.
yeah, some of it. So 3 divided by 2, you get 1.5, which is 11.
Okay. Okay. So what did you just said?
Yeah, exactly.
Okay, great. Thank you.
Yeah, always here.
Always here.